Hello, my name is Mr. Reynolds. Welcome to Calculus section 2.4. Today's topic is infinite limits, and we're going to look at what happens when a function goes to infinity. So here's a function, and as x approaches 0 from the left and the right, it's going to positive infinity. So instead of saying it does not exist, we would say the left limit equals the right limit, and it goes to infinity. So examples of this would be from the left and to the right, which is looked at that, goes to positive infinity. And this graph over here is actually talking about as x goes to negative infinity. So off to the left, it looks like the limit does exist. But if I was asked about the limit as x approaches a, which is right here, again we would say positive infinity. Here's some definitions. You can pause the video and read. This goes to positive infinity as it approaches a. This goes to negative infinity from the left and the right. Remember, limit definitions say it has to equal the left limit has to equal the right limit. So this goes to negative infinity, this goes to positive infinity. We could talk about right-handed limits. From the right side, this is going to positive infinity. From the left side, this is going to negative infinity. So examples of this: positive infinity, negative infinity. Here's a function. I cannot cancel or reduce. In order for the limit of 1 to exist, the left limit has to equal the right limit, and it does. So I would say A's answer is infinity. B is only looking at 3 from the left side. So from the left side it looks like I'm approaching negative infinity. And then C is actually asking for the limit, so I would have to look at the left and the right and see if it equals. Since the left does not equal the right, then I would say for C it does not exist because the right-hand limit is positive infinity. So once again, if the left limit does not equal the right limit, then the limit at 3 does not exist. This is kind of a concept that comes up every once in a while. If you have a number like 5 times a really, really small number, that will go to 0. If this gets infinitely small, then this number approaches 0. A big number divided by, or excuse me, a bigger number divided by a big number, not really sure what that does. It could potentially be a big number. But if this number is close to this, it could go to 1. But this does approach a very small number. So like 5 divided by a really big number, 9999999, is going to go to 0, or at least going to approach 0. This is going to approach negative infinity, a big number divided by any number. Over here, a number divided by a really small number like 5 over 0.00001 is going to go really big. This will go negative really big. And a really small number divided by a number just gets even smaller. So this is going to approach 0 again. This is kind of an important concept as we talk about this. Let me see if I can bring this to life for you. If I do x approaching 3 from the right and think about 3.0001, because I can't do direct substitution because I divide by 0, I could do direct substitution for the numerator. So I'll just talk about the numerator being 2 minus 5 times 3, negative 13. But in the denominator, I'm thinking about 3.0001 minus 3, which is 0.00001. which again, it's a number over a negative 13 over a positive small number. And we discussed on the previous slide that that would go big. In this case, negative big. Here again, I can't do direct substitution, but I still have negative 13, but this time I have a negative small number. So that would go to negative infinity. So the numbers I'm thinking of here, x approaching 3 from the left, would be like 2.9999. So this is like negative 0.00001. Analytically just means show the math. So I'm going to factor out an x and continue factoring. I can pull out an x squared from the denominator and reduce. So I've got the limit as x approaches negative 4 from the right. I'm going to be thinking about negative 3.9999. So I think I'll just do direct substitution for the numerator. So let's plug in a 4. 4 minus 2 and 4 minus 3. Oops, I'm so sorry. Negative 4. Negative 4 is negative 6 times negative 7. And we'll go for 42. Divided by, and this is where it gets tricky. I still have an x down below and an x plus 4. So this is going to be negative 3.999. And this is just going to be a really small number. So this is where that multiplication comes in handy. A small number times this gets really, really small. This is going to go negative small. And 42 over a really negative small number goes negative infinity. So any number divided by a small gets really big. Vertical asymptotes come from the denominator, but only if nothing cancels. If something cancels, it's called a removable. So for example, if you were to factor this numerator, you would get x minus 1, x minus 3. So if they ask for vertical asymptotes, you might think that it's a 1 and a negative 1, but this is actually called a removable. It causes a hole in the function. I'll show you an image of that. So the real function, when they ask for f of x, I'm really just thinking about x approaching 1 for x minus 3 over 1 plus 1. We're letting x be 1. So negative 2 over 2 or negative 1. So the only vertical asymptote would be negative 1. For this guy, the limit as x approaches negative 1 from the left, again, the function is x minus 3 over x plus 1. In the numerator, if I throw in a negative 1, I'll have negative 4 over, and this is going to go a really, really negative small number. So negative by negative is positive infinity. And then for the last one, it's going to be similar. It's going to be negative 4 over a positive small number, and that would be positive infinity. Again, the denominator is approaching 0, but you can't just plug in a negative 1. You have to look at negative 1 from the left, and this says approaching negative 1 from the right. So in the denominator, you have something like, or at least you're thinking of, negative 1.0001, and then plus 1, gives you that negative number in the denominator. Where down here, you're thinking of a number as x approaches -1 from the right, would be like -0.9999 plus 1, which would be a positive number. Again, here's that hole removable in the function, and the only vertical asymptote we had was at x equals -1. To evaluate cotangent, you can use some trig identities. Cotangent is really defined as cosine divided by sine. Looking at the unit circle, here's your cosine, here's your sine. You can evaluate the limit of cosine, but we have a hard time evaluating the limit of sine because sine is 0 and you don't want to divide by 0. So fortunately it's a right-hand limit, so I'll just do direct substitution. If I throw 0 in up here, cosine of 0 is 1. So it's 1 over 0, but it's not really 0 because I'm thinking of something really close to 0 from the right. So I'm thinking of like 0.000001. And so that's a really small number. And 1 divided by a small is a big. We could do the same thing from the left side, but this time I'd have 1 over -0.0001 because I'd be approaching from this direction, and that would be -infinity. Of course, some of us remember that the cotangent graph has 3 asymptotes. 1, 2, 3. And the cotangent graph, positive in the first, negative, positive in the third, negative in the fourth. So you can see from the right, it's positive infinity. And from the left, it's going to negative infinity. Evaluate the secant. I would do the same thing. I would change this to 1 over cosine. And let's find -3 pi over 2 on my unit circle. -pi over 2, -pi, -3 pi over 2. So I'm going around the circle backwards. The cosine is going to approach a 0 because cosine is the x-coordinate, sine is the y. And I'm approaching it negatively, so it's a negative really small number, which is a negative big number, infinity. Again, you could look at the secant graph. The secant is the inverse of the cosine, which I've graphed the cosine function here. But if I look at its inverse, it might make sense to you. Here's your -3 pi over 2. And from the right, it's going to negative infinity. You can pause the video and try these. Here I'd recommend you think about 2.99 minus 3 in the denominator. And then here you might be thinking about 3.001 in the denominator. And hopefully you'll get negative infinity and positive infinity. Here again, I'd recommend pausing the video and evaluating the limit as x approaches 1 from the left. So here's 1 from the left. It's going to positive infinity. So everything around 1 is going to positive infinity. This says 2 from the left, so that's also going to positive infinity. This one says 2 to the right, so that's here, so that would be a negative infinity. And since the left did not equal the right, in order for the limit to exist, here's your left-hand limit, here's your right-hand limit. If the yellow does not equal the blue, then the limit does not exist. This concludes section 2.4. Hope you found this video helpful. If you have any questions, please feel free to email me.